So now we're ready to find the Laplace transform of some power functions. But first, let's go ahead and write down the Laplace transforms that we currently have. So for some function y of t, I want to write its corresponding Laplace transform, which we can write as big Y of s. You'll recall when you took Calc 2, some textbook authors, when they found the antiderivative, they usually like to write big F of x. So if we'll accept, y, big Y of s as the Laplace transform. Let's recall that we found the Laplace transform of the function 1, and that had a Laplace transform of 1 over s, and e to the alpha t, and that had a Laplace transform of 1 over s minus alpha. And the condition, in the first one was that s be positive, of course, and here s is greater than alpha. So let's go ahead and start taking a look at maybe one of these power functions, like f of t is equal to, let's do like t squared, or something like f of t equals t to the 5th. And how do those things transform? So first, let's find the Laplace transform of just t. So I'll write it as the proper integral from 0 to infinity, e to the minus st times t dt. That's just the definition. So if I would integrate this, I would let u equal to t. In that event, du would equal to dt. So let's see, dv would pick up the rest. So again, I think this is a function, because I'm integrating by parts. I think it is as the product of a function and a derivative of some other function, to set up the integration by parts. We get dv is e to the minus st dt, so v must equal to the integral of e to the minus st dt. So I would get a negative 1 over s e to the minus st. So the integral of this u dv is going to be uv minus the integral of v du. So I'll write this as, let's write it below here. I'll write uv, so I would get the t times the negative 1 over s. I get a minus t over s e to the minus st, and I want to evaluate that from 0 to infinity, minus the integral of v du. So my du is just dt, so that's easy, but the v, I have a negative 1 over s, so I can make this minus a plus. 1 over s I can bring outside of the integral. There's no need for it to sit inside the integral, because only functions of time necessarily need to stay there. And then let's see, so my e to the minus st would go in, and then of course the du is just dt. So if we do the evaluation theorem for this minus t over s e to the minus st, at the upper limit at infinity, I'd get minus, so I have this t evaluated at infinity, but then it's multiplied by the decay function e to the minus infinity. And here again, we should recognize that the exponential function is going to decay a whole lot faster than the linear function, like y is equal to t. And so that thing should drive to 0, minus this minus is going to be a plus. When I plug in t is equal to 0, e to the 0, which is 1, I'll get 0 as well. So this entire thing just is 0. And then here I get a plus 1 over s. And the integral of e to the minus st is just negative 1 over s e to the minus st, and I want to evaluate that. I didn't put my limits of integration here, from 0 to infinity. And I've just dropped the limit notation as j goes to infinity, and I guess I could sort of reason what happens at really large values. So here, I guess I'd have a negative 1 over s squared, and then this will give me e at some negative large value minus e to the 0. Again, this goes to 0, this guy goes to 1. So in essence, I get a negative 1 over s squared times a negative 1 is just going to give me a positive 1 over s squared. So again, I assume that my s is positive. And here I see that my function t maps to 1 over s squared. So I want to keep going because as I had above, I really want to find, as long as s is positive, what t to any power maps to, or what its Laplace transform is. So let's see. I mean, already we had 1, which you can think of as 1 times t to the 0 maps to 1 over s, and then t to the 1 maps to 1 over s squared. Let's just see if we continue, if we start to see a pattern. So let's integrate from 0 to infinity. So I'm just going back to the definition, and then here I'll plug in a t squared dt. And likewise, I'll go through integration by parts. I'll let u equal to the t squared. I always want to reduce this power function. Here I get du equals 2t dt, and then my dv should be the same. So the dv picks up the rest, the e to the minus st dt, and v is going to be a negative 1 over s e to the minus st. And so let's just write this straight across now. So I'll get uv, that's going to give me t squared times the negative 1 over s. So it's negative t squared over s e to the minus st, evaluated from 0 to infinity, minus the integral from 0 to infinity of v du. So the v, again, is negative 1 over s. So I could put the plus 1 over s on the outside, e to the minus st on the inside. And in this case, du is a 2t dt. So times 2t dt. Now, I could have pulled the 2 out. I probably should. I should recognize that this is very similar to what we had done above, and I guess if you want, you can go through and show that that entire thing goes to 0. But the interesting part is that this gives me this 2 over s times the integral from 0 to infinity of e to the minus st times t dt. Well, that's the same thing that we found above. That's just the Laplace transform of t, this entire thing. Just the Laplace transform of the function f of t is equal to t. So what is a Laplace transform of t? So up here we say that t is, the Laplace transform is 1 over s squared. So I have 2 over s times 1 over s squared should give me 2 over s cubed. 2 over s cubed. Okay, so I mean, there's no real reason to continue in this, same vein, if you will. I mean, we can find t to many powers, but let's just convince ourselves, I guess, by finding the Laplace transform of t cubed. And after this, I'll write out the pattern that I see, and I guess many people before me have seen as well. So I get 0 to infinity. Here we get e to the minus st times t cubed dt. So in a similar fashion, we let u equal to the t cubed du. So you'll notice that this is the part that always goes under the radical. I mean, under the, not radical, under the integral, it's part of the integrand, when we do the integral of v du. And you notice that this constant always survives. So here we have a 3t squared. So before we had a 2, it survived, and now we have a 3. So let's see what happens. So du is 3t squared dt, and dv is going to be the same. So dv picks up the e to the minus st dt, and v is this. So I can write this out now as u times v. So here I'll get a negative t cubed over s e to the minus st, evaluated from 0 to infinity, minus the integral of v du. So v again was going to be the negative 1 over s, so this becomes plus something over s. I guess I'll pull that constant out. So I'll get v du. So my du has a 3 in there that I could pull out, but it also has a t squared dt. So I have the e to the minus st from v, and then the t squared dt from the du that remains in the integrand. Okay, so 0 to infinity. Well, if I look at this, this is just the Laplace transform of t squared. And if I multiply that times 3 over s, let's see, I just found out it was 2 over s cubed. I get times 2 over s cubed. That gives me 3 times 2, which is 6 over s to the 4th. But the real pattern that I want to hopefully see that has emerged is that the Laplace transform of t to any power, if I can keep on doing this, I can go to the 4th power, and then maybe it'll be a 4 times 3 times 2, and then to the 5th power, it'll be a 5 times the 4 times the 3 times the 2. So the power, I'll just write as n factorial. So in this event, I would have written as just 3 factorial, and I still would have gotten a 6. And at the bottom, let's see, in the case where I had 3, it seems to be the s to the 4th, like 3 plus 1. When I had a 2, it was 2 plus 1 or 3. I write it s to the n plus 1. So I write it up here as n factorial over s to the n plus 1 power.